Hello. This video includes information on oxidation numbers and balancing redox reactions.
Electrochemistry. This is chapter 17. It's stuff that you're going to see on the first part of your final exam. So when we look at electrochemistry, what we're essentially looking at is the relationship between the flow of electrons and what are called redox reactions. And redox reactions were covered in Chem 1 briefly, so we're just going to kind of build on that a little bit in Chem 2. So some examples of electrochemistry, we can look at what are called electrochemical cells, okay, which are cells that are set up in which we're looking at a product-favored redox reaction, okay, in the forward direction. Electrons are going to be generated and they're going to be transferred through an electrical circuit to cause an electric current. So we're essentially getting electricity from a chemical reaction. Okay, also when we talk about the corrosion of metals, that is an example of electrochemistry. It's a product-favored redox reaction. And then when we look at electrolysis, it is a reactant-favored reaction, meaning that the forward direction towards the product is non-spontaneous. And this will only occur in the forward direction if we force it to go. We have to add in an electrical current in order for electrolysis to take place. So it's a reverse reaction favored reaction. It's used for the production and purification of metals. It's used for electroplating processes. So we want to talk about what redox reactions are first. And by doing that, we need to first talk about what oxidation states or oxidation numbers are, because redox reactions have changes in their oxidation state. So when we look at a redox reaction, what that's really short for is an oxidation reduction reaction. But rather than writing all that out, okay, or saying oxidation reduction reaction all the time, we just call them redox reactions. And they involve the transfer of electrons from one species to another. So we have essentially two half reactions that are taking place in one redox reaction. So the first thing we have is what's called the oxidation part of a redox reaction. And that's defined as a loss of electrons. And when a species, an atom, an ion, whatever it is we're looking at, loses electrons, its oxidation number increases. And when we look at reduction, which is the second half of a oxidation reduction reaction or a redox reaction, we're looking at the half reaction that gains those electrons. And when the species gains electrons, the oxidation number decreases or is reduced. That's why it's called reduction. And when we look at these oxidation reduction reactions or these redox reactions, you can't have one without the other. If we have an oxidation taking place, if we have a species that's losing electrons, we have to have a reduction, which is a species that's gaining those electrons. So let's look at oxidation states. And first, just by convention, the sign typically comes first and then the number comes after. And there are rules for assigning oxidation numbers. And they're essentially a way for us to kind of keep track of electrons in a chemical reaction. Okay, and they represent the charge that atoms would have if we were looking at ionic compounds, although most of the time we're not looking at ionic compounds anymore. So here are some rules. If we're looking at an atom in its elemental state, okay, a pure atom, the oxidation number or the oxidation state is 0. If we're looking at a monatomic ion, the oxidation number is the same as the charge on that ion. And we can use the periodic table to figure out what those charges are. If we look at common nonmetals, okay, we kind of have some rules that we use to assign oxidation states. So for hydrogen, if hydrogen is with a non-metal, something on the right side of the periodic table, which more times than not it is, hydrogen's a +1 charge. If it's combined with a metal, it's actually hydride then, and its oxidation state would be -1. This is much less likely. For oxygen, in most compounds, oxygen has an oxidation state of -2. Now, it can be -1 if we're looking at peroxides. Okay, this is peroxide here. It's actually a polyatomic ion. There are 2 oxygen atoms and the overall charge is -2. So each one would have an oxidation state of -1. Peroxides are not nearly as common as just oxygen, which would be -2. Very rarely oxygen could be a -1/2. Okay, would kind of look like this, where we've got a polyatomic ion here, 2 oxygen atoms, and the overall charge is a -1. But not likely at all. Almost all the time, oxygen is a -2 for its oxidation state. Okay, when we look at halogens, those are elements in group 7 on the periodic table. Okay, fluoride is always -1 because it's got such a high electronegativity. The other halogens in that column are often -1, unless they're combined with oxygen or other halogens, and then they would have a positive oxidation state that would vary. And the last one is that the sum of the oxidation numbers or oxidation states, we can use those interchangeably. They can be called oxidation states or they can be called oxidation numbers. Okay. The sum of the oxidation numbers on all atoms in molecules will be 0 because molecules are neutral. And the sum of the oxidation numbers on all polyatomic ions will equal the charge on that polyatomic ion. So these are rules for how we assign oxidation numbers or oxidation states to atoms or ions in a redox reaction. So we're going to look at some examples. Let's look at the first one that's worked out for us. So we've got KCrO2. Well, K is a monatomic ion. That's potassium. It's an alkali metal in group 1 on the periodic table. All alkali metals have an oxidation number of +1. And there's only one of them in this formula. So I've got my +1 here. Now, chromium can have multiple oxidation numbers. There's no rule, no set rule for chromium. So I have an X in here. That's what we're going to figure out. Oxygen in almost all compounds has an oxidation number of -2, and there are 2 of them in the formula. So 2 times -2. The sum of the oxidation states, because this is a molecule, is 0. So now I'm just going to do some algebra. +1 plus X minus 4 equals 0. So I would add 4 to both sides, subtract 1, and that would give me X. So in this compound, chromium has an oxidation number of +3. Now, chromium has several different oxidation numbers it can have depending on what it's in combination with. So we have to figure it out. So let's look at the second one. We've got PH4 plus. All right, now we don't know P. Phosphorus is one of those, again, that has multiple oxidation numbers. Hydrogen can be +1 or -1. Since it's with a non-metal, it's going to be +1. There are 4 of them. But the sum on the oxidation numbers here is going to be +1, the charge on the ion. So we'd have our algebra. X plus 4 times plus 1. Each hydrogen has an oxidation number of +1, and there are 4 of them. And the sum is +1. Okay, so I've got X plus 4 equals +1. I'm going to subtract +4 from both sides. So the oxidation number on phosphorus in this compound is -3. So let's see how you can do on your own. Let's look at CrO4 -2. And you don't necessarily have to show any work. If you can do this in your head, that's great. Okay, we know oxygen is a -2, and there are 4 of them. We know the sum of the oxidation numbers for this ion is -2. What would chromium have to be? X plus 4 times -2, oxygen is always a -2, almost always a -2, equals -2. So we've got X minus 8 equals -2. Add 8 to both sides, X equals +6. Now notice that chromium up here was a +3. Chromium here is a +6. Chromium can have multiple oxidation numbers. It's one we'd have to figure out. All right, so hopefully we're getting the hang of it. Let's look at P4O10, tetraphosphorus decoxide. See if you can figure out what the oxidation state on phosphorus will be. Oxygen is a -2 in almost all cases. In this case, it is. 4 times X plus 10 times -2 equals 0. So 4X minus 20 equals 0. Add 20 to both sides, divide both sides by 4, X equals 5. All right, so let's try the next one. S4O6 -2. We want to figure out what sulfur is. Again, sulfur, like phosphorus or chromium, are multivalent. They have more than one possible oxidation number. All right, now this one's a little bit unusual. Most of them are whole numbers, but we've got 4 times X plus 6 times -2 equals -2. So 4X minus 12 equals -2. Add 12 to both sides. Okay, that and divide by 4. That does give us 5 halves, but positive 5 halves, not negative 5 halves, because we're adding 12 to both sides. Maybe yes, maybe no. Trick. Okay, chlorine equals 0. Okay, it's free element. It's not in a compound with other elements. Oxidation number is 0. Excellent. All right, so that's the first thing we have to be able to do. Now, we're going to start using that. We're going to look at single displacement reactions. So a single displacement reaction, one that you talked about at length in Chem 1, we're looking at an ion in a solution is displaced or replaced by a metallic element. So generically, here's our metal. Okay, something on the left-hand side of the periodic table. There is no M. We're just using that for our metal. Here's our ionic compound, XY. The metal displaces the positive ion out of the compound, and we produce My plus X. Now that's generic. Let's look at a specific one. Okay, iron, there's our metal. And we add it to a solution of copper sulfate. Well, since copper is a metal, it's going to displace the positive ion out of the compound. We're going to produce iron sulfate and copper. Now, the sulfates are spectator ions. So we really could kind of clean this up a little bit and cancel out the spectator ions. And we've got iron reacting with copper ions to produce iron ions and copper atoms. Again, we're just getting rid of the sulfates because they're spectators. Now look at what happens. The iron goes from an oxidation state of 0, because it was a free element, to an oxidation state of +2, because now it's an ion, okay? It's losing 2 electrons. Iron is being oxidized when it goes from a 0 to a +2 oxidation state. And where do these electrons go? Well, they can't just disappear. They're going to be gained by the copper ions. And the copper ions are going to go from a +2 oxidation number to a 0 oxidation number. The copper ions are going to be reduced. So we have an oxidation and a reduction taking place. This is a redox reaction. We have 2 electrons being lost by the iron, and those 2 electrons are going to be gained by the copper ions. Now, this is just a picture of it. When we look at copper sulfate in solution, it's a blue color. If we were to add some iron to it, okay, this reaction is going to take place. Notice the blue color goes away. It's because the copper ions are becoming copper atoms, and the copper atoms are actually plating out of the solution. And then they actually react in the solution and form something different. That's why it's not the color of copper. But we can see that the solution is no longer blue because the copper ions are become copper atoms. All right, so let's look at another one. And this time we're going to actually write it as 2 half reactions. So the zinc is going from a 0 oxidation number to a +2 oxidation number. Okay, how is it doing that? By losing 2 electrons. Losing electrons is oxidation. So zinc is being oxidized. Now our second half reaction, the copper ions are going to copper atoms. Okay, well, how are they doing that? They're gaining electrons, and gaining electrons is reduction. So the copper ions are being reduced. Now the electrons that are lost in the oxidation equal the electrons that are gained in the reduction. So that's good. And if we were to add these 2 half reactions back together, we would get a balanced reaction. No electrons are ever going to appear in the net reaction, net redox reaction. If the electrons lost don't equal the electrons gained, we have to make them equal by multiplying one or sometimes both of the half reactions by some coefficient. So let's look at this as an example. Okay, and actually the coefficients are already there. So if we would look at aluminum, aluminum is going from a 0 to a +3. Aluminum is being oxidized. It's losing electrons. Now, in this balanced equation, we have 2 aluminum atoms here and 2 aluminum ions here. Each aluminum atom is losing 3 electrons to go from a 0 to a +3. So if there are 2 of them, we're losing a total of 6 electrons. And if we look at the zinc, zinc is going from a +2 to a 0. Each zinc ion is gaining 2 electrons. That's why we have 3 zinc ions. So we have a total of 6 electrons being gained in the reduction, 6 electrons lost, 6 electrons gained. We have our balanced equation. Many redox reactions are more complex than that. And there's kind of a recipe for how we balance complex redox reactions. And if you just follow the steps like a recipe, you're going to be able to balance any redox reaction. So the first thing we do is we separate out the two half reactions. Then we do this series of steps in this order, and your redox reaction will be balanced. Okay, so we balance all of the elements except for hydrogen and oxygen first, and we do that by adding coefficients. Then we balance the oxygens by adding water. And the reason we can do that is because redox reactions take place in aqueous solutions. It's not like the water's coming out of thin air, it's taking place in water. So water can be part of that balanced equation. After we've balanced the oxygens by adding water, then we balance the hydrogens by adding hydrogen ions. And the reason we do that is because most redox reactions are in not just water, but they're in acidic solutions. So there are hydrogen ions available in order for the reaction to take place. And the last thing we do is we want to balance the charge, and we would do that by adding in electrons. And as long as we follow these steps, we're always going to have a balanced reaction. Now, we're going to assume right now that our reactions are in acidic solutions. We'll add a step on at the end if it says the question tells you it's a basic solution. So let's kind of follow the steps. So here is the reaction we want to balance. And the first thing we're going to do is write our two half reactions. All right. So we've got iron 2 ions on the reactant side going to iron 3 ions on the product side. And we have permanganate ions on the reactant side producing manganese 2 ions on the product side. So we have our oxidation and our reduction half reactions. And we're just going to go through the steps. So we assign oxidation numbers. We've got a +2 here and a +3 here. The charge on monatomic ions is the oxidation state. We have a +2 here. Oxygen's a -2. That gives us -8. The sum is -1, so manganese must be +7. Okay, just assigning oxidation numbers. Balance all atoms besides hydrogen and oxygen. Well, iron, there's 1 iron here and 1 iron here that's already balanced. Over here, there's 1 manganese here, there's 1 manganese here, so we don't have to do step A. It's already balanced. B, balance oxygens by adding water, then balance hydrogen by adding hydrogen ions, then balance electrons to get the charge balanced. All right, so let's look at our oxidation half reaction first. Okay, there are no oxygens, so we don't have to add water. There are no hydrogens, so we don't have to add hydrogen ions. We have a +2 charge here and a +3 charge here, so we have to lose 1 electron. Okay, it's an oxidation half reaction because we're losing an electron. The oxidation number is going up. Now, let's look at our reduction half reaction. It's a little bit more involved. Okay, we want to add water to balance oxygen. So there's 4 oxygens on the reactant side. We're going to add 4 waters on the product side. Oxygen's now balanced. Now we're going to balance hydrogens by adding hydrogen ions. Well, we've got 8 hydrogens on the reactant side. So if we add 8 hydrogen ions, we've balanced our hydrogens on both sides. And again, we can do that because these redox reactions are taking place in an acidic solution. And then we want to balance the charge on both sides. I'll look up here first. Actually, let's look up here. Let me get rid of. There we go. Okay. We have a -1 charge here. And we have a +8 charge here. That means the reactant side is a +7. On the product side, we have a -2 here, and we have a 0 here. So the product side is a +2. We have to get the charge equal on both sides. And we would do that by adding 5 electrons to the reactant side. So now we've got a -1, and a -5, that gives us a -6, and a +8, that gives us a +2 on this side to go along with a +2 on this side. Now our charges are balanced. So we balanced oxygen by adding water, balanced hydrogen by adding hydrogen ions, and balanced charge by adding electrons. Now, in the oxidation, we're losing 1 electron, but in the reduction, we're gaining 5. They're not equal. So what we're going to need to do next is we're going to have to multiply the oxidation half reaction by 5. Okay, we can do that. 5, 5, 5. And the reason we do that is so that the 5 electrons that are lost in the oxidation equal the 5 electrons that are gained in the reduction. Because when we write our overall balanced redox reaction, there shouldn't be any electrons in there. We're forcing the electrons to cancel out by multiplying by coefficients. And then we can go through and double check that our reaction is balanced. It needs to be balanced for atoms, and it needs to be balanced for charge. We've got 1 manganese here, 1 manganese here. 8 hydrogens, 4 times 2, 8 hydrogens. 5 iron, 5 iron. Okay, so atoms are balanced. We've got a +8 and a +10. That gives us +18. -1. That gives us a +17 on the reactant side. We've got a +15, 5 times 3, a +15 and a +2 and a 0. That's a +17 on this side. So we balanced for both atoms and charge by going through these steps. So let's try another one. Okay, first thing we want to do is we want to write our 2 half reactions. Okay, so we've got H2C2O4 yields 2 CO2 plus 2E minus. Now, there were 2 carbons here. That's why we've got a 2 here. Okay, plus it gave it to us here, but that's where that comes from. The oxidation state on, did I put it here? I did. The oxidation state on carbon here is a +3. The oxidation state on carbon here is a +4. So each carbon is losing 1 electron, and there are 2 carbons. So that's where this 2 is coming from. The manganese is going from a +7 here to a +2 here. So our reduction is gaining 5 electrons. All right, now we want to balance oxygens by adding water. Well, we've got 4 oxygens here, and we've got 2 times 2, we've got 4 oxygens here. We don't have to add water into this half reaction. When we balance hydrogens, we've got 2 hydrogens here, so we need to add 2 hydrogen ions here. And then we've got a 0 charge here, and we've got a -2 and a +2, we've got a 0 charge here. You don't necessarily have to put these electrons in here, you can put them in down here. It doesn't matter which way you do it. Okay, so now if we look at our reduction, we have our manganese already balanced, 1 on each side. We have 4 oxygens on the reactant side. That means we're going to add 4 waters on our product side. We have 4 times 2. We've got 8 hydrogens on our product side. So we're going to add 8 hydrogen ions on our reactant side. And then we've got a +8 -1, that gives us +7, -5, that gives us +2, and we have a +2 and a 0 on the product side. So our charges are balanced. Now, for the oxidation, we're losing 2 electrons, but for the reduction, we're gaining 5. We have to make those two numbers equal to each other. Well, 2 and 5 have 10 in common. So if we take our oxidation half reaction and multiply it by 5, everything, that's going to give us 10 electrons lost. And if we take our reduction half reaction and multiply it by 2 times 5, that's going to give us 10 electrons gained. So our electrons gained will equal our electrons lost. And we always make that happen because the electrons have to cancel out. So we distribute this 5. So 5, 10, 10, and 16, 2, 10, 2, and 8. Now, electrons lost in the oxidation equal electrons gained in the reduction. That's going to cancel out. We have 16 hydrogens being gained here and 10 hydrogens being lost here. We want to write a net number of electrons in our net equation, in our overall equation. So these 10 hydrogen ions would disappear. 10 out of the 16 here would disappear, and we'd be left with a net of 6. So we get 5 H2C2O4 plus now just 6 H plus. It's the net, 10 and 16. The net is 6. Plus 2 permanganate yields 10 carbon dioxide plus 2 manganese plus 8 waters. Again, we can double check. We've got 16 hydrogens on both sides, 28 oxygens, 10 carbons, and the charge is balanced on both sides. So we have a balanced redox reaction. All right, so let's look at this one. We've got zinc going to zinc ions. We've got dichromate going to chromium ions. Well, this one's already done for us. That's pretty easy. Okay, actually, I don't want to do that. Okay, so we've got the reduction half reaction here. See if you can follow the steps and balance that equation. The chromiums have to be balanced first. That's why there's a 2 here. Now balance the oxygens by adding water. Then balance the hydrogens by adding hydrogen ions. And balance the charge by adding electrons. And see what you get for that half reaction. We've got 7 oxygens, so we have to add 7 waters. That gives us 14 hydrogens, so we have to add 14 hydrogen ions. And then we've got a plus 14 minus 2, that gives us a plus 12. We have a plus 6 on this side, so we have to add 6 electrons. Now, electrons gained in the reduction is not equal to electrons lost in the oxidation. So think about what you have to multiply the oxidation half reaction by to get electrons lost to equal electrons gained, and then add up and see if you get a balanced equation. All right, so we need to multiply the oxidation half reaction by 3. So this becomes a 3, and a 6. Electrons lost equal electrons gained, and then we add them up. Okay, the charge will be 12 on the reactant side and 12 on the product side. We've got 3 zinc, 14 hydrogen, 14 hydrogen, 2 chromium, 2 chromium. We've got 14 oxygen is wrong. That should say 7 oxygen. We've got 7 oxygens here and 7 oxygens here. That should say 7, not 14. All right, now, sometimes we're going to see some problems that say the redox reaction's in a basic solution. All right, we're going to balance it as if it's acidic, and then we're going to do one step at the end, which will change it to be a basic solution. All right, so we want to break them up. We've got perchlorates going to chlorate. The chlorines are balanced. There's 4 oxygens here, only 3 oxygens here, so we have to add a water. There's 2 hydrogens here. We have to add 2 hydrogen ions here. We're going to balance it as if it's an acid. And then we're going to add a -2 charge to give us the charge being balanced. That gives us a -3 plus 2. So we have a -1 on the reactant side to go with the -1 on the product side. Now, this one's easier. Okay. The rubidiums were already balanced. There was no oxygen, so we don't have to add water. There's no hydrogen, so we don't have to add hydrogen ions. And there's 1 electron being lost. Okay. Electrons gained have to equal electrons lost, so we just multiply everything by 2. Okay, add them together. So this is how the reaction would be balanced if it was in an acidic solution, but it tells us it's a basic solution. So this is how we're going to fix it. For every hydrogen ion that's in our balanced equation, we're going to add a hydroxide ion to both sides. And the reason for that is the hydrogen ions will react with the hydroxide ions and make water. So since we have 2 hydrogen ions here and we want to make it a basic solution, we're going to have to add 2 hydroxides here to cancel out our hydrogen ions. And if we add 2 hydroxides, that's going to give us 2 waters on the reactant side. And we have to add 2 hydroxides to the product side to keep it balanced. So we add 2 hydroxides, that gives us 2 waters. And we add 2 hydroxides on the product side. You can't just add something to one side and not also add it to the other side, because then it won't be equal. Now, we've got 2 waters on the reactant side, and there's 1 water on the product side. Okay, when we write net equations, you can't have the same thing on both sides of the arrow. So this 1 water will cancel out with 1 of the 2 waters here, and we're going to be left with 1 water. Now, look at the reaction the way it's written now. There's no hydrogen ions in here anymore. That's what made it acidic up here. And there's hydroxide, which tells us it's a basic solution. So if it tells us in the question that we're looking at a basic solution, we're going to balance it as if it's acidic, and then we're just going to fix it at the end to make it basic. And again, it's balanced. We've got a -1 charge here. We've got -2 and -1 that gives us -3 plus +2 that gives us a -1 on this side. 2 hydrogens, 2 hydrogens here, 1 chlorine, 1 chlorine, 4 oxygens. There are 3 here. Sorry. Oh, sorry, 5. 4 plus 1. There's 5 oxygens here. 4 plus 2. There's 5 oxygens here. 2 rubidium, 2 rubidium. So we have a balanced equation.